Hello, welcome back. In this segment, I'm going to talk about linear congruence. Suppose you're given an equation like 4 times x is congruent to 2 mod 6. Your goal is to find the value of x. How can you go about it? Let's first run this thing and I'll explain the idea in a moment. As you can see, 5 and 2 are the two possible solutions. So when you plug in 5 here, 4 times 5 is 20. 20 mod 6 is 2 because 20 divided by 6 will give you remainder 2. And 4 times 2 is 8. 8 mod 6 is also 2. So these are the two solutions. 5 and 2 are the only two solutions. Okay. You can confirm yourself whether there are any other solutions, but you will not find anything other than 5 and 2. But on the other hand, let's take something like, say, for example, 2x is equal to 1, right, in mod 4. Okay. In this case, you will not find any solution. There's no solution because 2x is an even number. When you divide an even number by 4, you will not get 1 as a reminder because what you're trying to say is 2x can be written as a linear combination of 4 times something plus 1, which is not possible because 2x is an even number and 4 times something is also even number. So you will not get any solution for this equation. Okay. All right. So now the question is, can we formalize this and explain under what circumstances we expect a solution, and when a solution is found, how many solutions can there be? Okay, so I'm going to formalize this notion now. All right, that should be easy because we talked about linear Diophantine equation, and I will show you a very nice trick that you can convert this problem into other problem, a reduction. Basically, we like reduction in computer science. Convert one problem into another problem. Suppose your goal is to solve a times x congruent to c mod m. Okay, your goal is to find x which satisfies this equation, congruence rather. How do we now make use of the linear Diophantine equation we learned about earlier? So congruence 1 is nothing but a times x plus some m times y equal to c. It must be clear why, because if you take mod on both sides of equation 2, this part will cancel out. Then you will get a times x is congruent to c mod m, which is what exactly equation 1 says. So 1 and 2 are equivalent. Okay, but we know how to find solutions to equation number 2 because we just learned from linear Diophantine equation how to solve that. Okay, that's basically it. You convert this equation into this equation from 1, reduce it to 2, solve that, and we don't need to worry about the solutions for y because y is not of interest, right? Our goal is to solve this equation. So we can just discard the y that comes out from linear Diophantine equation. We don't care. And as I mentioned earlier, when will the Diophantine equation have a solution? Okay, an equation will have a solution only if the GCD, right? So remember the notation we talked about in the previous segment. Let me quickly write it here. General equation a times x plus b times y equal to c will have a solution in integer solution for x and y if the GCD of a and b, d must divide c. If this is true, then we can always find an x and y. Okay, that means in this case, instead of b, we have m here. That means the GCD d, which is equal to GCD of a and m, which we can easily find using Euclid, for example. If this GCD, okay, if d divides c, equation number 2 has a solution. It's an equivalent constraint, not only one direction, both directions. Okay, if d divides c, we know for sure equation number 1 will also have a solution. If equation number congruence 1, if congruence 1 has a solution, the GCD of a and m must divide c. Okay, that's something we already established in the previous segments. Okay, now the question is, let us assume d divides c. The question is, how many solutions are possible to the congruence shown on number 1? Okay, so we can easily see, let's say somehow we found one solution, okay, using Diophantine equation, solving the Diophantine equation 2. Let's say that equation, we thrown away the y, we don't care. So let's say x0 was a solution to congruence 1, okay? That means a times x0, when you divide it by m, you get c as a reminder, okay? So what are the other solutions possible? So you can actually easily extend it, just the same idea of linear Diophantine we talked about. The other solutions are m by d. We know m, we know d. D is just GCD of A and M. Okay, you can now wait one moment. I will show you why these are all other solutions. And 2 times M by D and so on until x0 plus D minus 1 times M. I'll explain why I say this is a set of possible solutions. Okay, these are the only possible solutions for the congruence 1. Okay, if we know x0 is one solution, which we can easily get from solving the de Fontaine equation, then we can generate all other solutions. So how many numbers did I write? I have up to D minus 1. That means D minus 1 over here and then 1 because of this first one. So I have D solutions. So this congruence 1, if there is a solution for x, there are D such solutions. This is important. D solutions possible. Okay. What is D? D is GCD of A and M. All right. So now let's talk about why these are the solutions. Okay. Let's talk about why we have these D solutions. Let's just take one example. Let's take x0 plus I times M by D. Okay. I is some integer. Okay. So x0 plus some integer I times M by D. Let's multiply that by A because we are going to check this is a solution, right? So A times this in mod M. Okay, let's see what happens. Okay, A times x0, we know A times x0 is nothing but C because we checked x0 as a solution. We assumed x0 as a solution. That means A times x0 mod M will be nothing but C. So this is nothing but C plus A. Let's write it I times A by D times M, right? Okay. We do know D is GCD of A and M. Therefore, D divides A. Okay. This implies D divides A. That means this is going to be an integer. This whole thing is going to be an integer. And it's a multiple of M. Okay. So when you do mod M, this is going to be canceling out. So you get C, which is exactly what we need for a solution. So I took arbitrary number from this collection and I shown you informally that that collection is a solution. Okay. So why did I stop at D minus 1 M by D? Why didn't I not continue? Let's say I added one more solution plus D into M by D. Well, D and D will cancel out. And what will we get? We get x0 plus M, which is same as x0 in mod M, right? Because M will become also cancel out in mod M. So we have back to x0. Okay, so that's basically it. You have D solutions. If the congruence 1 has a solution, there are D solutions. Otherwise, there are no solutions. Okay. Now I'll show you the implementation very quickly. This is what I did. I actually used the linear de Fontaine that we talked about in the previous segment. I called it as a linear de Fontaine equation to be solved. As you can see, my B is nothing but M. Okay. So basically, I'm solving A times X plus M times Y equal to C. That's what I'm solving using linear de Fontaine equation. Okay. And then if there's a solution, then I extract the GCD. That's the first component that I get out from my linear de Fontaine equation. And then I have a loop that goes through all the solutions that I shown you on the whiteboard, X plus I times M by D, right? All in mod M because we are working in modular arithmetic. And that's basically it. So this is what I drew on the whiteboard, right? For I equal to 0, you get a first solution, I equal to 1, second solution, and so on. So this loop is going to run from 0 through D minus 1, which means D times. Okay, that's basically, as I said earlier, D solutions. All right, so we do know how to solve linear congruence equations. Okay, thanks to linear de Fontaine equations, we can easily convert congruence into de Fontaine, throw away the y because we don't care about the y. We only care about the x, and we can generate all possible solutions easily. Once the solutions exist, it's easy to generate. Okay. We only need one solution. As you can see, X is the only solution I get from my linear de Fontaine, and then the rest is just I times M by D. M is the modulus, and D is the GCD of A and M, okay, between A and M. All right, that's basically it. Thank you very much.